Dear students, welcome to the course Bioprocess Engineering. In the previous class, we have studied the basic requirements of a fermentation process, design requirements of a reactor, and various types of bioreactors designed to meet the demands in biotech industry. Today, let us proceed with another interesting and most needed topic in bioprocess industry. With a heavy breakfast, we start our day and continue to do our work up to the noon, and we feel hunger after noon. Having a sip of coffee or tea in between activates our regular activities, and we won't feel hunger at our regular lunch time. Intermittent addition with some of nutrients aids to regulate the metabolic activities. When hospitalized needing trips, glucose will be injected continuously to regulate our metabolic activities. The time span of carbohydrate uptake has a major impact on regulating the metabolic activities in our body. Thus, the mode of addition of carbohydrate into a bioreactor in turn affects the yield of bioprocess. Cultivation of microorganisms is one of the most important activities of any fermentation process. Success of the bioprocess lies in our ability to maintain high cell density, particularly it is more so with the growth associated processes. The bioprocess may be carried out in various types of reactors with different flow characteristics. Depending upon the type of reactor, the growth characteristics varies. Today, we will be studying the growth characteristics of microorganisms in batch, fed batch and continuous cultivation systems. A batch system is characterized by flow pattern in which there will not be any flow rate of inlet or outlet. That is, all the contents are fed at once initially, into which a small quantity of cell culture is inoculated and the inlet and the outlet valves are closed. The cells lives in an environment initially which is rich in nutrients, medium and substrate. This gives a very congenial environment for the organisms to grow and divide. Practically, the cell division occurs after initially passing through an acclimatization phase which we call as the lag phase. The growth of the organism in the batch system of cultivation gives the characteristic growth curve with lag, log, stationary and the dead phase. The cells starts multiplying exponentially in the exponential phase where the growth rate of the organism is given by Malthus law, which states the change in biomass concentration with respect to time is directly proportional to the biomass concentration, and the proportionality constant is the specific growth rate of the organism. As the cell growth increases, the number of cells will increase with time by consuming the nutrients, medium and the substrate. In other words, with the progress of time, the concentration of nutrients and the substrate will decrease, with the result that the cells are starved of the nutrients and their growth rate will decelerate, which is known as deceleration zone or stationary phase. The stationary phase will occur if the substrate or one of the substrate is limited in supply. Such substrates are called limiting substrates and their concentration are known as limiting substrate concentration. As the limiting substrate concentration increases, the specific growth rate also increases, and further increase in substrate concentration does not show any increase in specific growth rate, which we call as maximum specific growth rate, where in the stationary phase, as no growth occurs, the growth rate of organism is 0, that is, there won't be any change in biomass concentration during the stationary phase. The stationary phase is further followed by the dead phase, whereas the decrease in biomass concentration is proportionately equal to the initial biomass concentration and which is guided by the specific death rate constant. The growth rate of organism in the batch system of cultivation can be easily understood by plotting different graphs in terms of logarithmic values and change in concentration of cells. In summary, there won't be any inlet or outlet during a batch system of cultivation and the volume of the reactor remains constant, but there occurs a rapid change in biomass, substrate and product concentration. The advantage of the batch system of cultivation is that pure cultures can be obtained with less contamination levels, but a drawback batch system of cultivation is that the toxic metabolites that are being produced during the process can be toxic, can be retarding the growth rate of the cells. In certain cases, the substrate that is added to the reactor might be in high concentration, inhibiting the growth of the cells, and the products that are being formed in the batch system of cultivation might be an inhibitor affecting the growth rate of the cells, wherein the substrate inhibition and product inhibition are two major challenges in batch system of cultivation. Fed batch systems are one of the most commonly used flow systems in bioprocessing. The fed batch system can also be considered as a semi-batch system where there might be periodic inputs into the system. The culture materials are fed continuously to a batch system and the process is allowed to proceed, wherein in a fed batch cultivation system, the volume of the medium increases in due course of time. Semi-batch operations are carried out in which one of the reactants is fed continuously or one of the products is removed continuously or all the reactants are added continuously. The fed batch reactor systems are carried out to prolong the log phase of the cultures, wherein the growth rate of the cells is enhanced, wherein the biomass concentration that is obtained from this system is very high compared to batch system of cultivation. As the medium is added into the reactor, the medium gets diluted and the dilution rate is the major limitation with the fed batch cultivation systems. An interrelationship between dilution rate and biomass concentration is given. The change in biomass concentration is proportional to the dilution rate in the reactor. An increase in cell density can be obtained with the fed batch cultivation systems, and these fed batch cultivation systems are commonly used with the recombinant cells, in which the recombinant cells requires more protein concentration for the cells to grow. In a fed batch cultivation system, the volume of the reactor will not be constant throughout the process and there occurs changes with biomass, substrate and product concentration with respect to time. With substantial changes in biomass, substrate and product concentration in due course of the process, the batch and the fed batch cultivation systems are recognized to be unsteady state process. As can be seen in the batch and fed batch cultivation system, after the log phase growth of the cell culture, the cell growth reaches a stationary phase as the medium concentration decreases. Suppose we devise a system in which the medium is added continuously, then obviously the cells never feel the dearth of nutrient and hence they grow continuously. However, there is a difficulty. This system of cultivation or considered to be open system of cultivation wherein there is a continuous contact of the system with the surrounding. A typical bioreactor that is being used for continuous cultivation systems is shown, wherein the fresh culture medium is fed into the reactor at a constant flow rate, and the product and the unused medium will be continuously taken out from the system at a typical flow rate. A simple flow scheme is given wherein the flow rate of the system is governed by the peristaltic pump, and there is a continuous productivity inside the reactor wherein the biomass, substrate and product concentration remains to be a constant, making the process to be a steady state. The dilution rate, represented as D, is the ratio of volumetric feed flow rate into the reactor and the volume of the reactor. As in the batch phase culture, the substrate and the biomass concentration varies with time, but whereas in the continuous system of cultivation, the biomass and substrate concentration remains constant throughout the process. A maximum specific growth rate is obtained by continuous monitoring of dilution rate inside the reactor. The continuous system of cultivation can be carried out in a turbidostat where the turbidity of the cells is maintained constant throughout the process, and in the second mode the concentration of chemical entity inside the reactor is maintained a constant. Medium will be fed in the constant rate, and the dilution rate determines the specific growth rate of cells. The basic difference between turbidostat and chemostat, or the method of growth rate control, is internal in turbidostat whereas it is external in a chemostat. The growth rate of culture is at or close to maximum specific growth rate, but whereas in a chemostat it will be from just above 0 to just below maximum specific growth rate. The biomass concentration will only be increased if the control settings on the photometer are changed, whereas in a chemostat increase in biomass concentration can be observed. The culture volume and the environmental conditions remains a constant in both turbidostat and chemostat. The duration of cultures will be indefinite in both turbidostat and chemostat. The mutants that provide maximum specific growth rate are used in the turbidostat, wherein the mutants that can withstand high dilution rate are used in the chemostat. In a nutshell, there is a continuous inlet and outlet of mosses into and out of the reactor in order to maintain a constant volume, biomass concentration, substrate concentration and product concentration. As all the variables remains to be a constant value, the continuous cultivation system is called to be a steady state process. To summarize, the biomass concentration increases with respect to decrease in substrate concentration in the reactor, and the substrate concentration reaches 0 as the biomass concentration enters into the stationary phase, wherein in the fed-batch system of cultivation, the substrate is fed into the reactor continuously at periodic intervals, and the substrate concentration never reaches 0, hence the biomass remains in the log phase. Whereas in the continuous system of cultivation, there is a continuous inlet of substrate into the reactor, and the biomass is withdrawn from the reactor at a typical flow rate, wherein the substrate and biomass concentration remains constant throughout the process. The microorganisms can be grown in the reactor under three modes of cultivation: batch, fed batch, and continuous system. The growth characteristics of the cells are limited by the mode adapted for growing the cells. In the fed batch and continuous system of cultivation, the dilution rate and the substrate concentration are the limiting factors that affect the maximum specific growth rate of cells. Thank you.